All right. All right, everybody. Hi, and welcome to another great Tuesday. It's still really warm outside. Yesterday we had flooding, and I hear the weather is not going to be any better. So, for those of you living in more interesting parts of the state or the country, welcome, and I'm hoping you're dry and not, well, it's really hot. Right, so today we're going to talk about describing data. Last time we talked about the way we could present data using frequency distributions and histograms, and the way we could talk about aspects of that data. Today we're going to start talking about the way we describe data and hopefully start chapter 3. So when we talk about describing data, we have to consider how we look at data, and the way we should be looking at data is the way we should be looking at, well, let me get the, excuse me. The way we look at data is the way we should be looking at say this, right? We can give it some this. Now, if this was representative of a histogram of sorts, or even just a frequency distribution, we could say a couple things about this, right? What could we say? Well, we could be looking at all this massive set of data, right? And we could say, hey, this has some center, right? If I asked you where this data is located, right, it could be like, well, it's this long, right? And it looks like it's centered here, so if I was going to pick it up, I would probably drag it here, right? We have some variation, right? Some places have very little data, some places seem to have a lot, right? Some places are a little denser, some people are a little bit less spread out, right? So we have this kind of spreading. We have, as I said, kind of a center cluster of it. We could look at it and say, hey, this has some kind of a distribution, right? Either we consider this kind of a loopy around or up, down, kind of, right? So depending on how we think about it, we could be looking at it like, hey, hang on, there's one more here, right? And we could consider this to be an outlier, like, what the hell are you doing here? Shouldn't you be somewhere here, right? So this kind of outliers. And then the last thing, which we won't talk about in class a lot, but it's something worthwhile to keep in mind, is questions, how is this changing over time? Is there some specific way this has changed from the last time we had it to now? Because change over time gives us another dimension to be looking at this data, because now we are no longer looking at this as a picture, we're comparing it to the picture before, picture before, and we get kind of a cartoon movement happening of the data, right? There's something happening between the peaks, the way it's distributed, the way it overall varies, and that's worthwhile information. Yeah. So, well, let's make a list. We should probably. So, if we are talking about data, so describing data, there is the 5 characteristics we mentioned. Well, first of all, we have the center, right? If you're looking at an object, first question is where is the center of mass, right? Even if you're not looking at center mass, you're looking at the center of the object. If I asked you, look at this lid, where are you going to be looking at? You're not going to be looking at the edge. You're going to check the edge out, but you're going to be looking at the center of this. So this has some center. 2 is variation. And the question is this uniform? Is there ups and downs, right? Is there a shape to it? This one seems to have an edge, so there's difference between this and the edge, right? Third one is distribution. And distribution, it talks about how is the data overall set up. Is it up, down, or is it just, if you look at this side, is it completely flat, right? So that's distribution. Then we can look at something called outliers, and outliers are pieces of data that seem to be very different from the rest of it, right? If you have a squad made out of jocks and cheerleaders, the person with the glasses that listens to some obscure band and is somewhat geeky is an outlier. It's different, right? It's if everybody in your family is, say, Catholic, and you have one cousin who is Buddhist, that seems different. I'm not saying worse, and I'm not saying bad, I'm saying different. So outliers are those points of data that just seem somewhere out of a perceived range where things should be based on the rest of the data. And then the last one is change over time. And there is considerable amount of information one could get out of change over time. Alright, so if there is no more, I'm not seeing any questions. Damn, I'm still talking to myself. Alright, so we're gonna start with the most basic one, which is the center. Well, the center is also, if you consider it, the middle of the data set. And there are 3 ways to see the center. Well, one way, which is I suppose the most obvious one, is we're going to just look at the mean. And what the mean is, it's just the simple average. And we all calculated that before, so there shouldn't be any issues. And what is an average is, right, it's the sum, so a mean equals the sum of all values that we are considering divided by, well, the number of those values. Super. So we have this way to look at. Well, let's introduce a slightly more mathematical notation for this. So to do that, I am going to introduce couple terms. We say X is the data value, Now x is a representing for the whole group of data values, and according to what value x equals to, it's the data value we are talking about, right? So if we have a set of heights for people and we define height as being x, that x changes value depending on which data point we're looking at. Then we have n, which is the number of values in a sample. And again, when I say values, that could also mean items, right? This could mean number of objects. It's the count of how much is in your set that you're looking at. And then, since we know populations and samples are different, capital N is the number of values, items, in a population. So that's this. And then we have x bar, which is we define as the sample mean. And then we have mu, which is the population mean. And this is like a U with a longer nose. We pronounce it mu. Mu. It's usually written as mu. So, all right. So this is the basic setup. Also, looking at this, our sample mean would be what? Well, it would be sum of data values. This character is a capital letter sigma, and that means sum. So whatever follows this character should be just added up. And in our case, x follows that character, which means that after the capital sigma we have an x, which means add all the values of x together. And we can very easily do that because we have, say, a table to do it. So that means sum. Divided by number of values. Well, if we are talking about a sample, then sample number of values is n. And that's that. And then population average equals to, well, again, we're looking at all the values divided by, well, number of all the values. All right. So this is the basic. Just check. Yep. All right. So now let's look at the expansion of that. Let's look at a simple example. So if we were talking about heights, right, let's look at the heights of markers, depending on which marker you have. And you have some collection of markers, and you want to know what is the average height of those markers. Now, well, how do we do it? Well, we can take a ruler and we can measure them out. So we measure them out, and they come out to be 5.4 inches, 5.3 inches, another 5.4 inches. Oh, we got a shorter one, so we got one of those cute ones at 3.7 inches, and a couple bigger ones, 6.2 and 6.3. So we have some collection of markers. So how do we do the average? Well, the average for this is the sum of all the x's divided by n. Well, easy enough. 5.4 plus 5.3 plus 5.4 plus 3.7 plus 6.2 plus 6.3, and we come out to be 32 divided by 3. Now, how many of those markers are there? 1, 2, 3, 4, 5, 6. So divided by 6, we come out with 6 right here. We come out with 5.38 inches. The average marker length is easy. And here comes the question, what does this mean? Well, this means the mean, also means the average, but it also has one more meaning which will become important later, is that if I reach into my low cup of markers, what am I expecting to get? Well, I'm expecting to get a marker about 5.38 inches. So this is also the expected value, right? If you went on say Bumble and you started swiping right, and every date you had was 5.7, or the average of those heights was 5.7, wouldn't you expect the next date to be also 5.7, right? It seems to be consistent. This way of calculating center has one weakness though, and that one weakness comes from the fact that what happens if to all this I add one more marker, and I have one of those, Dave and Buster's huge marker at 23.1 inches. What happens if I add that to this? Well, let's take a look. Our mean was sum of all the x's divided by n. 32 plus 0.3 was the sum of all those, and then we added one more marker to this whole set, so we have to add one more x to it, and now instead of just 6 we have 6 plus 1 because we added one more. And now we do this little calculations, 3 plus 23.1 divided by 7, and we get 7.91. And suddenly, just because we added a very large number by comparison, the average changed drastically. And here's the big problem with means and averages and expected values. The big problem of that is that if you add numbers which are much bigger or much smaller than the set, the average is going to be greatly affected, which means that means are greatly affected by outliers. We haven't covered what an outlier really is, but we all have a good feel what an outlier could be, because the moment we see it, we're like, oh, that is an outlier. All right, cool. So that's first set. Should I zoom in? Let's go with this. Right. All right. So this is here. Right. So what's the other way? Well, a way number 2 to find a center is median. And I am convinced that every single one of you heard that term before. You usually hear it in respect to median household income, or median household sale price, or median life expectancy, or some other ones. Household income and house prices are are the most common one. So what is a median? Median is the middle value of a data set. It's the middle value. That's it. Well, how do we get it? Well, first of all, if we are talking about a middle value, we probably should, to be exact, we must order the data set. And what does mean order data set? Well, make it from smallest to largest in a ascending order, or from largest to smallest in a descending order. So we have to sort the data. Second one, we need to find the middle value. And how do we find? Well, if we have a set of values that looks like this. Eight, 3, 5, 11, 13, 4, and 6. What's the middle value? Well, if we order it, it's 3, 4, 5, 6, 8, 11, and 13. Well, where's the middle value? Well, the middle value is right here, smack in the middle. That's easy enough. So finding middle value. So if odd number of values, right? 1, 2, 3, 4, 5, 6, 7. If we have 7 values, if it's an odd number of values, median is the middle value, and in that case is 6. And what happens if this set looks different? What happens if an ordered set looks the following: 3, 4, 5, 6, 8, 11, 13, and 74. Well, let's see. 1, 2, 3, 4, 5, 6, 7, 8. What happens if it's an even number of values? Well, where would be the middle? Well, 1 here, 2, 3, 4. So it's suggesting that the middle value should be here, right? That's the middle of this whole thing. So what we do is we take the average of those two values. So 6 plus 8 divided by 2. 14 divided by 2, 7. The median is 7. So if it's even number of value, median is the average of two middle values. Okay, so this should make sense. You know what? I'm gonna do this. Zoom it in a little bit, since I've been doing a lot of writing. So this is the basics. Now here's the interesting part, is if you look at 74 feels like an outlier. It's really far from this single and low double digits numbers here, right? If we consider this, for example, monthly salary of 3 grand, 4 grand, 5 grand, 6 grand, 8 grand, 11 grand, and 13 grand, 74 grand feels like very different, right? Prices of used cars, again, 74 grand feels very different. So this has a feel for an outlier, and we know that if we calculated the mean, this would screw with this a lot. And yet the median did change. It became slightly larger, but only slightly, right? So the median is not affected by outliers the way the mean is. And that's the beauty. That's the reason why medians are used to calculate household incomes. Because if, Bezos or Zuckerberg or Bill Gates moved into your neighborhood, the mean income in your neighborhood would skyrocket, even though everybody is still making the same amount of money, with the exception of having one much more well-off member of the public living there. On the other hand, median, your pay, the average income in the neighborhood would go up, but not enough to cause a stir, which means we might have a much healthier view on what actually is going on. And again, both of those methods of finding a center are valid, and both of them have a different use. We use mean if we want to consider all the data and we are actually curious, about things that are very different. Median, on the other hand, we use when we want to see where the density kind of the data is lying around, where we have more of the data packed. Okay, that's median. Right. And the last one we're gonna talk about is the mode. And mode is the most common data, or the most commonly occurring piece of data. And and we have some examples here. The mode for the first one, well, there is no mode. All the data values are as common as all the other data values. In the second one repeats twice, so the mode is 1, and we have one mode at 1. And in the third one, we have 3 9s and 3 1s, which means that this is a bimodal data set, which has 2 modes at 1 and 9. Now, one has to be careful because some computer programs and certain calculators online will see a data set that looks like this as bimodal, having 2 modes, one at 1 and one at 9, because it looks at which sets of values repeat the most, rather which repeat the most singular, right? In this case, 2 of them, but they're both repeating at 3, where here it's repeating 3 times, repeating 2 times. So one has to be a little bit careful, but overall, mode works that way. I think my mic is too loud. Is this better? Better. All right, I think this is better. Sorry, I just saw the volume bars clip a little higher. So, all right. So this is the basics for center. Now that we are starting to do some mathematics, a couple rules about the math part. rounding. It's a good practice not to round during the problem. So rounding only on the last step of a problem. And second good practice is to round to one more decimal. To round to one more decimal place more than the data. So if the data is asking you about say heights and they are 5.6, 6.2, right? Your answer, whatever the answer may be, should have say 5.12, one extra decimal place by comparison to what the question was asking. If you don't know how to handle this or you have a hard time with this, a good rule of thumb is 2 to 3 decimal places. I prefer this, but I will accept this. Again, I am much more interested in you being able to do something with this data rather than just you focusing on calculations. Okay. All right. So let's look at if we can do something fun with this. So first things first. Let's deal with the mean of a frequency distribution. And let's say we had a set of data, ages, that looked the following: 21 to 30, 31 to 40, 41 to 50, 51 to 60, 61 to 70, and 71 to 80. And since it's a frequency distribution, let's add some frequencies: 28, 30, 12, 2, 2, and 2. Okay, so how do we do it? Well, first of all, we cannot deal with an average of a set directly. Well, why not? Well, we cannot deal with this because 21 to 30, there's 21 to 30, 28 people that are 21 to 30. What does it mean? Is there 28 21-year-olds, 28 30-year-olds, or is there 10 of each or 2 of each, or is there it's just you don't know how this data looks like, and there's several ways we can deal with it. What we can do is we can assume that we have a data value that will represent this whole set, right? And one of the ways we can do it is we can look at the midpoint. And a midpoint for this is the average of those two numbers. So that's 30 plus 21 divided by 2. In our case, 25.5. What I'm saying is I am guessing that, or I'm assuming, or I'm hoping that this data is uniformly distributed. And if you remember, uniformly distributed means it looks like this rather than, say, looking like that or looking like that, right? It's uniformly distributed. So we have the same amount of 21-year-olds, 22-year-olds, 23-year-olds, 30-year-olds. So I'm assuming that everybody in this group is about 25 and a half years old. And I can do this for the rest of the groups. Now, do I have to calculate this average for all those groups? No. I know that the class width is 10, right? Two lower class limits, which means that the class width between the midpoints should be the same, 10, 10. So this becomes 55 and a half, 65 and a half, and 75 and a half. Super. All right, so now we need to consider how many 25 and a half year olds are there. Well, there's 28 of them. So combined, there's 714 years. Those two are adding to the total number of years in this frequency distribution. Why are we doing that? Well, if you remember the definition of a mean, it's the sum of all the x's. Well, there's 28 of 25 and a half year olds, right? So I have to multiply that plus the next one, right? So what I'm aiming at is that this. The sum of all the years added together divided by what? Well, this divided by the total number of people that were there. Well, in that case, sum of all the frequencies. And so if we do that, well, let's sum them up. Sum of all the frequencies, if we add this up, should be 76. And then sum of all those, so sum of x times f should be 270. Yeah, that looks about right? Again, I can do this because I'm guessing and assuming that the age in this uniform distribution is this. Right? So I'm using the class midpoint because there's nothing else I have access to, right? I could assume 21-year-olds, but then if there's more 30-year-olds, I'm screwed. If I consume 30, then I'm overestimating. So I'm just picking the middle. All right, so this gives us all the years in this table divided by all the people in this table. And here comes a question which sometimes I like to ask. What happens if the actual average for this is 37.12? Right? This number, this average, means that under my current assumption, the average age of people in this frequency distribution is 35.76, right? Or if I wanted to phrase it differently, no, I think that's the best way. The average age of these people is this. Well, if the actual data gives me that, why is there a discrepancy? Well, the discrepancy is because here we made an assumption of what the age in each one of those classes was, where here we had access to the raw data. So if you have access to raw data, your answer is going to be a lot more precise and can be significantly different than what you got making the assumption. Now again, both numbers suggest that the average is somewhere in this class, which would make sense. There's a lot more people 21 to 40 than there is 41 to 80. On the other hand, an 80-year-old person brings 4 times as many years into the mix as a 21-year-old. Right? So this kind of suggests that the balance should be somewhere in the middle of the table, right? Somewhere around here, right? Because this suggests that the suggests a little bit of a graph like this, right? 700, 1,000, there's some 500 here, and there's 100 to 130 and 150. It's some shape like this. Well, right, the center of the data should be somewhere in this middle, which is 31 to 40. So again, it's all about how we're looking at data. Okay. Let's. All right. Well, now that we are starting to draw pictures, I suppose we should look at some of them. Normal distributions are very common in our lives, but not all of them are as symmetric as one would expect. Sometimes they look like this. Right? This is a normal curve. It's a bell-shaped symmetric curve. Right, bell-shaped symmetric. So this is this. Now, this piece of data, this set of data, right, has this long tail on the left side. So this piece of data is skewed, which means for some reason there is some more data on the left side skewing the picture. On the other hand, this one is skewed right. Again, we had some distribution, and there's some pieces of data here which are dragging the tail out, and that skews the data. Well, let's take a look at. I'm gonna use black for mean and red for median. If we looked at the top, the mean and the median should be right in the middle. They should be right in the middle because it's symmetric, so the number of data values ends up in the middle, and the mean should be in the middle because, add all the big ones, smallers, and all the things in the middle, averaging somewhere in the middle. It should inherently make sense. Now, on the other hand, if we skew the data left, which means we add small values, the mean should drop. And depending on how fast and how big the difference between the low data values and the rest of the data set is, it will drop more or less. On the other hand, the median will drop as well because we have more values on the left, but will it drop by as much? No, because median is resistant to outliers. Same thing here. If we add a couple really high values, the mean is going to go up drastically, when the median just moves up a little bit from the middle. It's one way to think about skewed distributions. It's how the mean and the median align. All right. So that's this. All right. I am going to take a quick break. I need to drink some water. I'm seeming to lose my voice. Um, I'll be back in about 3 to 5 minutes, and then I'll continue. See you soon. All right. Thank you. I noticed that if I run 2-3 hour long recordings, my voice suffers a lot, so I'm gonna try to make a short break every hour or so, just so I have time to have a sip of water and cough things up without interrupting the stream. All right, so let's talk about the next thing on our list. Where's our list? We talked about center, so the next thing is variation. All right, so let's talk about variation. And what is variation? Variation is talking about how the data is spread. Right? Is it all wide or is it all grouped up? Like, think about this. You go to a shooting range, and are your shots all grouped up, or are they all kind of spread apart? And that makes a difference, right? So this is what a variation talks about. So what can we look at? We could look at archery, I suppose. So say you want to look at archery, and well, we have couple shooters, number A, number B, number C. So we have those 3 shooters, and each of them fires 3 arrows. And what can we have? Well, we could have the first guy fire 3 arrows and get 5, 5, and 5. I think that's not bad setup, hit 3 times. We could have a second guy, try to better himself, and he could fire a 3, a 6, and a 6. It's not bad. Well, the last person comes up to shooting, and they fire a 1, a 4, and a 10. And you're looking at this kind of shooting aspect, right? Those 3 shots, and well, right at this point, the only way we know how to look at data is find the center. Now let's see. 5 plus 5 plus 5, 15 divided by 3. I'm gonna use what? That's 5. Okay. Second, 3 plus 6, 9 plus 6, 15 divided by 3, 5. 1 plus 4, 5 plus 10, 15, 15 divided by 3, 5. So as far as the center of the data is concerned, these data sets are not different, and yet they do feel different, right? You have a consistently shooting 5, decent shooting 6s, sometimes missing, and well, this is a complete whack-a-mole. So there's several ways we can look at the variation of data in this, and one way to look at it is we can look at the range. And by what I mean by the range, I mean the range of the archery shot, I mean the range of the data, and the range is calculated in the following way. We take the maximum value minus the minimum value, which is easy. I used to have a boss like this who would come into the meetings and be like, hey, I can calculate the range for you. And I'm like, oh, thank you very much, boss. We all can do that. Right, so we're looking at the maximum value minus the minimum value. So range, rise, that gives us a set. Well, maximum value 5, minimum value 5, right? So the range here is 0. Maximum value 6, minimum value 3, range is 3. And the last one, 10 minus 1, 9. Okay, it gives us some variation, tells us that those three things are differently spread apart. But there's one problem. What happened to the middle value? It feels that the 4 should matter. It should matter if it's close to 1 or if it's close to 10 or if it's right smack in the middle. So this doesn't consider all values, right? It just looks at the top and the bottom, which in small data sets, squint your eyes is quasi okay, but in large data sets, if you have 1,000 data values and just looking at the top and the bottom, I love scooter gangs. If you just look at the top and the bottom on a 1,000 values data set, that just feels awkward, because what happens to the other 998 data values, right? So there's a problem with it. Well, then we have a second one that we can look at, and that's the standard deviation. And the standard deviation measures the average. Of what? Well, of the distance between a data value and the mean. Well, data values and the mean. The average distance. Okay, well, this is great. Couple things. It should be never 0. Right? If you have any variation in your data, this standard deviation should not be 0. Right? Which exception of, well, all data values are equal. Right? Because if all data values are equal, there is no variation. This standard deviation turns into 0. So there's a little caveat here. It's not negative, because by definition distance cannot be negative, right? The distance between this marker and this marker is something, just like this and this marker is. There's a distance here. It cannot be negative. This is not a negative of this. The direction changed, but it's not negative. So it's not negative, and well, this is an average based on a mean, so it feels like outliers are going to be a problem. So okay, so this is let's zoom out a little bit. Give me some more space to work with. So this is the basic premise. All right. Oh, so let's see. There is a formula for population standard deviation. So population standard deviation has a symbol, and it's a small sigma. It looks like a cannon, and that is the sum of sorry, I got too excited. Sorry. Again, that's the distance between the data value and the mean. We square it because we don't want negative values. This wind is getting to me. Let's see if this will work. We square it because we don't want negative data values. We divide by n because it's an average, and then we take a square root to get rid of this. That's the formula. And then for sample standard deviation, we have S equals to sum of x minus x bar squared divided by n minus 1. And we should probably talk about this minus 1 here. And the reason why minus 1 is here is because if we take a sample, we are looking at a slice of the whole pie, which means that we have to be very aware that the variation that in the whole population could be different. So we are overestimating it, right? If we are talking about a population, we know exactly how many data values there are, and we are accounting for all of them. So the difference between those two is this is a potluck or kind of a friendly get-together. So if you're preparing food and getting paper plates, you're going to take more because somebody's going to bring a +1 that they didn't tell you about, or somebody's going to bring their kids, and so you are overestimating the variation. Where this is a wedding with an RSVP, you know exactly how many people are coming, so you know exactly how much food there should be. And that's the difference between those. This -1 is here, so you overestimate the variation of the data because of your sample. There's a second formula that we can use for sample standard deviation, and that's this one. And although it looks a lot bigger and a lot scarier, it provides for the exact same answer and is easier to execute, especially on large data sets, mostly because you don't have to calculate the mean. So we will use both of those. So let's do some calculations of standard deviations for this data set. So do I have another color marker? Well, Kingdom for a blue marker. Let's see. Well, that's an epic fail. I can't find my blue marker. Oh well, I'm gonna try to use this fake dark one, see if it works. Alright, so for the first one, since all the data values are the same, the standard deviation turns out to be 0. So that was easy. Let's calculate the second one. Let's put this here. Use this, and with the formulas. Let's put the formulas here. Let's write them down. Alright, so we have the formulas, we have the data set. Let's do a calculation. I'm going to calculate B using the first formula. So we're going to do S equals to sigma x minus x bar squared divided by n minus 1. Well, what do we need for this? Well, we need a set of x's. Well, let's see, 3, 6, 6. We need some mean. Well, we have the mean as 5, so we have that. Next one, we need this parenthesis here, so x minus x bar. Well, 3 minus 5 minus 2, 1, 1. What's next? We need to have x minus x bar squared. -2 squared, 4, 1, 1. Great. What else do we need? Well, we need the sum of this. So sum of x minus x bar squared equals to 4 plus 1 plus 1, 6. And then we need to produce this, which is s. The top part is 6, the bottom one is n minus 1. How big is our n? N is size of 3 because we have 3 data values. 3 minus 1, 2, and that's a square root. So this equals to square root of 3. And if anybody is curious, that's about 1.73. And so we got our standard deviation at 1.73. That's dreadful, but okay. Alright. So that's how we could calculate the B. And I'm going to put it right here so we don't lose it. Alright, so let's calculate C using the second formula, which is n sum of x squared minus sum of x squared, the whole thing, n times n minus 1. Now let's see, what do we need? We need an x. Excuse me. Alright. Stop moving already. That's the problem. I keep the window open because otherwise it gets unbearably hot in here and the wind comes in. Stop. So we need x's. Well, we have a set of x's. It's 1, 4, and 10. What else do we need? Well, we need x squared. 1 times 1, 1. 4 times 4, 16. 10 times 10, 100. Do we need any other columns? No, we don't. We need the sum of x's. Well, so sum of x equals 15. What else do we need? We need sum of x squares. 117. We need n, and that's still equals to 3. Okay, let's fill it out. S equals 3 times sum of x squares, 117, minus sum of x squared, so 15 squared, divided by 3 times 3 minus 1, 2. So S equals 330 plus 21, 351, minus 15 times 10, 150, 5 times 15, 50, 75, 75, so 400 and 225. Okay. And divide by 6 square root. Well, let's see. 351 minus 205. They do it right. Minus 225 equals 126. So S equals to 126 divided by 6 square root. Divide by 6, that comes out to be 21. So the square root of 21. And square root of 20. Of 21, 4.58. 8. Yeah, this marker is dead by my marker. All right. So we got a set of values. And again, as expected, C has bigger variation in data than, C has bigger variation than B, and B has slightly bigger variation than A. And A has 0 variation because all the values are the same. Again, calculations are straightforward. As far as proving to me that you know how to do this, I would like you to show me once on one example that you are capable of doing this, and then after that you're more than welcome to use any standard deviation calculator that you want or want to use. Fancier calculators than this have it built in, but you can find a bunch of online calculators that are just as good at doing this. The only thing you have to understand that some of them will calculate population standard deviation, some of them will calculate sample standard deviation, and those two results will be different. So if you are doing it using a calculator of some sorts, you have to be aware which one it is. I will not ask you to do standard deviation computations on the final, because that's cruel and unusual non-punishment. You either know how to do it or you don't, and that will come out in your future jobs anyways. So this is this. All right, let's talk more about it. Sorry about this. I'm using recycled paper for this. So I picked up a bunch of old pieces of paper that my campus didn't need, and some of them are old syllabi and whatnot, so they're for some reason stapled together. Every now and then I run into a problem like this. All right. So now, what is standard deviations good for? Because we calculated it takes a little bit of time to do it. So why? And the reason why, which will become much more obvious in chapter 3, but we should introduce it now, is the look at what the standard deviation tells us. And what it does is that if a piece of data, right, if an object in your data set, so if a piece of data, right, or a data value, right, is within 2 standard deviations of the mean, right, which means that if the mean is here, 2 standard deviations this way or 2 standard deviations in this range, if this range, this piece of data, we consider it to be usual, which means that yes, there is variation in the data, and the variation in the data should be within 2 standard deviations. So either it's a little smaller or a little larger, but there's a very clear window. So in our case, right? If this is the average, 2 standard deviations is about 3.4. So a usual piece of data would be 5 minus 3.4 or 5 plus 3.4, and everything in between those two values, so everything between 1.6 and 8.4 would be considered usual data. We're going to do examples. And if outside 2 standard deviations, we call it unusual. I'm not saying weird, but it's unusual. And then if it's 3 standard deviations, we sometimes refer to it as very rare, because it just shouldn't, you shouldn't be finding pieces like this very often, right? You walk down the street, what are the chances you're meeting a billionaire? Well, there is some chance, it's just very rare. And this allows us to think about the empirical rule. So there is this rule which says the following. It says if empirical rule for normally distributed data. So if we have a data that is normally distributed, the empirical rule says that 98% of data is within 1 standard deviation away of the mean. No, okay, let's visualize it. 68. So if we have some normal distribution, we know the mean should be somewhere in the middle. 68% of the data is about this. This should be 68% of the data, which means what's on the bottom? Well, on the bottom we have, say, some mu plus sigma. Mu is somewhere in the middle. And here we have mu minus sigma. That same works for a sample as well. So all this section is within just 1 step. Then we have that 95% of the data is within 2 standard deviations away of the mean. Which means what? Well, which means 1 standard deviation. Here's 2 standard deviations is here. So that's mean plus 2 sigma, and that's mean minus 2. And all this section, that's 95% of all the data, right? So usual things are within the 95, and unusual things are in the remaining 5%. Well, we can go 1 step further. 99.7% of the data is within 3 standard deviations away of or from the mean. Which means that if we extend this a little bit more, all this is 99.7%. What does 99.7% mean to you? Well, 99.7% means 3 out of 1,000 are not. Right? We're talking about rare data, very rare pieces of data that are right outside of this set. We also can look at things slightly differently. We can say, hey, how much data is between the mean and 1 standard deviation up? How much is this red piece? Well, this red piece is half of 68. So this is 34%. Why? Because this is a symmetric curve, which means that I can do certain things like this. I could ask you, how big this piece is. How big is this piece? Well, this whole thing was 95, so half of this is 95 divided by 2%, which is 47.5%. Right? So you can do certain things with this. But this is empirical rule at its core. It's question of how much data should be between those. And again, that gets tricky when we have a small data sets, because in small data sets you either have a very small or very large standard deviation. If your data set grows larger and is relatively consistent and ends up having a normal distribution, you can do empirical rule rather comfortably. So that's empirical rule. All right, what can we talk about next? So let's mention something else. When you read statistical papers, or you read papers in general, you might encounter a term called variance. And variance is referring to a way we can talk about variation of data. And so variance has the following formula. For sample variance, the formula is S squared. S was standard deviation, so the variance is the square of the standard deviation. Population variance is sigma squared. So we can very easily go from variance to standard deviation, from standard deviation to variance, just by taking squares and square roots. So if our standard deviation was 1.2, the variance is going to be 1.44, because S squared equals to 1.2 squared, which gives us this. On the other hand, if our variance was 4, our standard deviation equals to 2. Why? Because standard deviation equals to square root of sigma squared, which is square root of 4, which equals to 2. So that's variance. Alright. Let's close out the variation. If data is grouped together, we expect our standard deviation to be small. And I'm saying small with quotation marks because that's not very precise. It's more of a it's small by comparison to what it could be. If the same data set is spread around, okay, this wind thing is getting annoying. If the data set is spread around, then we would expect the standard deviation to be large. So that we have to keep this in mind. So if you see a very small standard deviation, you're expecting a very tightly packed data. If you see a large standard deviation, then you expect the data to be all over the place. And the larger it is, the more all over the place this is. Alright, so that's that. Alright, so let's start using this, because there's some information we can gain on it. So what happens if we happens if I have those two pieces of data? I have a height average of 65 inches with a standard deviation of 3 inches and a weight of 175 pounds with a standard deviation of 4 pounds. Well, which one has a bigger... Oh, excuse me. Sorry about that. Apparently the dogs wanted treats, and they were given treats in the wrong orders, or they thought they were giving the wrong orders, and they decided to sort it out between themselves. I swear, small dachshunds are like low gang members. There's a hierarchy, and I haven't caught up with what the hierarchy is, so every now and then they tend to resolve their disputes Jerry Springer style. Everybody's okay, nobody got hurt, no animals got hurt. They got their treats, and suddenly it's peace and quiet. Anyways, back to this. If we ask about which has higher standard deviation, that's easy. Weight does. Which one has more variation? Standard deviation, easy. More variation? This one has a 4, this one has a 3. 4 is bigger than 3. But if we are comparing 4 and 3, you know, gain 4 pounds, gain 3 inches, lose 4 pounds. Apples and oranges, right? This feels very much like apples and oranges. So we cannot really compare 4 to 3 for variation. So what can we do? Well, we could do something called the coefficient of variation, which says S divided by X bar times 100%. which means that we're going to compare this to the average and standard deviation to the average and come up with this. So coefficient of variation for the first one comes out to be 4.62 and percent, and the second one 2.9. This, I haven't seen this very widely used. It shows up every now and then. It's an easy way to say, hey, this varies more based on the total, center mass of the data, where this varies less. It varies more by just kind of comparing numbers, but relative to how big this whole set is, this is much less of a difference. So that's coefficient of variation. Alright, so that is it's nice, but it's not great, because it would be really nice if we could measure relative standing in a consistent way between or within data sets. So we had a consistent way to do it, and for that I will introduce you to the bane of your existence called the z-score. You're gonna love it, because for the rest of the semester this is all going to be all over the place. So the z-score, and the z-score says the following: it's the number of standard deviations a data value x is away from the mean. So the z-score for populations x minus mu divided by sigma, and for sample it's x minus x bar divided by s. Let's see, is there any questions? No. Well, I suppose not. All right. So this is it. So, for example, if we looked at a data set, what can we use? Well, we could use, let's use the weights here. So if we have x bar equal to 175 lbs and a standard deviation of 4 lbs, and we have some data value equal to 182, what's the z-score for that? Well, the z-score is x minus x bar divided by s. So in our case it's 182 minus 175 divided by 4. So that comes out to be 7 divided by 4, right? Which comes out to be 1.75, if I got it right. Yep. Which means that this data value is 1.75 standard deviations away from this, which means that we can say, hey, this data value is a usual data value. It's within 2 standard deviations. It's more than 1, but less than 2. So it's a usual piece of data. Right, so that's a relatively easy calculation. And we can do that to a lot of things, so that's relatively straightforward. Alright, let's try something else. What happens if we pull a data set out of it that weighs, say, 100. So let's look at x bar equal to 175. 5, an S equal to 4, and an X equal to 150. Well, okay, so the z-score for that is 150 minus 175. Again, it's always x minus x bar divided by s. The value minus the average divided by the standard deviation. Divided by 4. So a z-score comes out to negative 25 divided by 4. So that comes out to be negative 6.25. Yep. Which means what? Which means that our data value is smaller than the average. Check. How much smaller? Well, 6.25 standard deviations, which means that it's extremely rare that out of a data set which has those descriptors, a standard deviation of 4 and an average of 175, to find a piece of data that is this far away. Is it possible? Yes. Is it very unlikely? Yes. This is extremely rare piece of data. There's not a lot of them. Alright, so that closes up z-scores. Let's seriously. Alright. And looks at least quasi-professional. All right, so now let's talk about quartiles. And quartiles, there's 3 of them. There's the first, there's the second, and then there's the third. First quartile referred to as Q1, represents the bottom 25% of sorted data. Right? So if we have our data arranged in a line from smallest to largest, first quartile represents the bottom 25%. Second quartile, also referred to as Q2, isn't very often referred to Q2 because it has a different name, and it's called the median. Represents the bottom 50% of sorted data. Why is it the median? Well, because median was the middle value. If median was the middle value, then this is 50% of the values, this is 50% of the value. Median is right in the middle. So that's Q2. And then third quartile, referred to as Q3, is the bottom 75% of sorted data. Okay, so let's look at an example. The example we're going to use is 1, 3, 6, 10, 15, 21, 28, and 36. Well, where's the median? So first we're going to calculate the median because this one is easy. So 1, 2, 3, 4, 5, 6, 7, 8. 8 values, which means that the median is going to be right in the middles here. And the median is 10 plus 15, 25 divided by 2, 12.5. So that's the median. And then we're going to divide the bottom and the top, in the same way we did the median. So we're going to take all of this and all of this, and we're going to divide those the way we would divide a median. So we're making a median of a median, right? You cut something in half, and then you cut it again in half, you're going to get a quarter of the whole thing. So if we divide this, our Q1 will come out to be 4.5. And again, we're going to divide this, and our Q3 is going to turn up to be 24.5. Right? So check if it's ordered, and if not, sorted. Find the median, and then find Q1 and Q3. So check if ordered or sorted. 2, find median. 3, find Q1 and Q3. Alright, well, let's see if we can do that. Let's look at another set of data. 1, 2, 3, 7, 8, 9, 11, 17, 1, 2, 3, 4, 5, 6, 7, 8, and 92. Alright, well, where's the median? 1, 2, 3, 4, 5, 6, 7, 8, 9. So the median in the middle is right here. And now we're going to calculate the quartiles. We don't include the median, so quartile 1 will be here, quartile 2 will be here. Sorry, quartile 3 will be here. We don't include the median, because if we include the median, we are overreaching, so it's better to underreach than overreach. So Q1 will be here, and that's 3 plus 2, 5 divided by 2, 2.5, and the second one will be here, Q3, 11 plus 17, 28, 14. Easy. Takes practice, but should be easy. And again, this. Now, fair warning that some online calculators and some programs calculate quartiles and medians slightly differently. They don't sort it and pick out the middle value. They have some way to estimate it. So every now and then you might get results which are a little bit different. So one program might calculate quartiles differently than another. They're all going to be very close to each other, but they won't be the same. So just a heads up that with very large data sets, certain programs will estimate quartiles versus actually doing what we do, which is hand picking the values. Again, we will not work on excessively large data sets. So I'm making a mess. All right. So let's make it a little bit more fun. Let's look at percentiles. And there was a question about percentiles from one of the students. So I'm going to try to do my best to provide enough information for them to be able to solve the problem. So percentiles are not percentage. Those two things are very, very different. So that's one. So percentiles say, hey, I am going to cut my data into 100 pieces. If I'm going to cut it into 100 pieces, I'm going to have to make 99 cuts. Right? Just like if you want to divide data into 4 pieces, it's enough to do 3 cuts to it. It's the same idea. So there is a 99 percentiles. And which means that the highest percentile you can be is 99. 99th percentile. If you ever took SATs or any other of the standardized tests, you will see this. 99th percentile means you are better in whatever that thing that was testing it is. You're better than 99% of individuals. I'm gonna say tested, but whatever that measurement was. So you scored better than 99%. You cannot, and I'll underline it, be 100th percentile. That's impossible. And the reason why it's impossible, because 100th percentile means you're better than everybody, including yourself. It's a kind of a metaphysical part. So that means you are better than everyone and you. You cannot be better than you. You are you, kind of thing. So this is kind of a no-go. So 100th percentile is bad. So if anybody gets upset with you that you scored in the 99th percentile, they're like, why aren't you in the 100th? Because metaphysically you cannot be better than yourself right now, kind of thing. So, all right. So how do we calculate this? Well, we calculate this the following way. So the percentile of x equals to number of values less than x divided by total number of values. Now we need to make a percentage, so times 100%. So, for example, if you scored say 71 out of 100 points on an exam, and say 42 out of 45 people scored below you, what's your percentile? Well, 71 divided by 100, that's your percentage. But your percentile would equal to 42 divided by 45 times 100. Which comes out to be 93rd percentile. And each one of those has some merit to be used. This is telling you how did you score according to the answer key or the perception of the test. This is telling you how well you did comparing to everybody else. If you are the smartest or the biggest fish in a small tank, you're going to have a very high percentile. But if you're a medium fish in a really, really big pond, you might not be the biggest fish around. Right? So this is comparison. For SAT scores, they they used to tell you how many answers did you get right, and that gives you a percentage of how well you did according to the test. And then this gives you a relative standing comparing to everybody else, which might be a considerably better measurement of how well you know. But if you end up taking SATs in a year where everybody is doing really well, you're gonna fall behind. On the other hand, if you take a test at the time where a lot of people way lower on academic level are taking the test, you're gonna do surprisingly well. So it's one of those, if you end up taking the exam with a bunch of dummies, huge percentile, and your score doesn't matter, even if you did very well or if you did poorly. On the other hand, if you take the exam with a bunch of super smart people, your percentage might be through the roof, and yet you might still fall behind because of your percentile. So there is some usage for both side of this coin. I don't know which one's better. This one, if the tests are very fair and very well balanced, this seems to be better because it measures you independently. This one is much more of a rat race because it compares you to everybody else. All right. What else can we do? We could ask, what is the 25th percentile? What is that? Well, that is Q1, because that means this number separates the bottom 25%. So that's Q1, right? Percentile for the 50th percentile is the median, or Q2, and then 75th percentile is Q3. So if we just look at the percentiles, we have a vague idea of where it is in the data set. All right. Then we can look at something called the 5-number summary. And 5-number summary has the following aspect: has a minimum, a Q1, a median, a Q3, and a maximum. And that should be relatively easy to find out. If we look at this data that we just covered in the earlier, what's the minimum? Well, the minimum is 1, Q1 is 2.5, median is 8, quartile 3 is 14. What's the maximum? The maximum is 92. And what does this? This gives us an ability to draw something called the box plot, or box and whiskers plot. There's a couple names for it. So if we were to draw it out, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 15, 20, 25, 20, 25, 30, 35, 40, 45, 50, 55, 60, and so on. And let's call this 90. This is 0, 1. Let's call this 1 and 0 somewhere here. All right, and that's 5 and then 10, 15. All right. So if we were to draw it out, we will start with minimum. We would move to the first quartile. So this is minimum, Q1, and we draw this line and this. Then we draw the box plot all the way to Q3, which is Q3. You know what? let's make it nice and pretty. So we start at 1, we draw it to 2.5, that's here, so that's minimum Q1, and we draw it to 10, 20, 14, which is Q3, and then we draw this all the way. Why did I pick 90? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let's call this 92. I don't want to draw it anymore. Right there. And here's the data. And that's the max. And then the median ends up being so you draw a box and whiskers plot. Alright, so first things first, one can quickly realize that this allows us to tell where the data is concentrated. Well, because this space right here and this space right here and any of those little slices contain 25% data. So there's 25% of data in the first section, 25% of the data in the second, 25% of data here, and 25% of the data here. This seems very concentrated. It's very short, which means that there's a lot of data packed next to each other. Then those two are about the same size, and then this one is like way out, which means that the data in this section is very much spread around. So box and whiskers plot gives you exactly that. It gives you an ability to very quickly tell me how the data is kind of spread around. Because if we had a box plot that looked like that, well, I can tell you that there's about the same amount of data in each one of the quarters. But if you got a box plot that looked like this, right, which is our case, it tells me that this is occupying a lot more space than this. This data is spread around a lot more. And you can have all the kind of different combinations of sizes, and each one of them tells you a little bit of information about how the data is lying around. So I think box plots are pretty cool. They're not used as well. They're just kind of there and everybody ignores it, but there's a lot more you can get from a picture that looks like this, and a picture that looks like this, and a picture that probably would look like this. So depending on where that line is and how big it is. So that's box plots. And 5 number summaries. Easy stuff. And then we get to outliers. Outliers, which are pieces of data that are away from everything else. And to find outliers, we need to find something called IQR. This is an I. My J's are much fancier. So this is an IQR. And IQRs are defined the following. So an IQR is defined as Q3 minus Q1. That's how IQRs are defined. Then, this is step 1. Step 2, we need to calculate the following. 1.5 times IQR. And then step 3, we finally find the borderlines for the outliers, and those are Q1 minus step 2 and Q3 plus step 2. So again, let's look at our data. IQR in this case would equal to Q3 minus Q1. So in our case, that's 14 minus 2.5, which comes out to be 11.5. So that's our IQR. Step 2, that's step 1. Step 2 would be to multiply this one times 1.5. 11.5 times 1.5. So 1.5 IQR equals to 17.25. And then the last step will be to find those two. Q1 minus 1.5 IQR and Q3 plus 1.5 IQR. Well, Q1 is 2.5 minus 17.25 comes out to be negative 14.75. And then 14 plus 17.25 equals to 31.25. And what is this telling us? It's telling us that any data value smaller than this or larger than this is an outlier. Means the data point is different enough from what? Well, from this little piece, the middle 50% of the data, right? IQR talks about the middle 50% of data, right? It's talking about this range right here. So if a piece of data is somewhere way below, kind of this space, so anything above this or anything below here would be an outlier. Well, in our case, 92 is an outlier, and anything above this would be an outlier. Oh, this should be somewhere here, but either way. And what do we do? Well, there's a decision to be made. You could ignore outliers. You could list them as something that skews your calculations. You could make two tables with and without outliers and compare them and let somebody else make the decision. There's a lot of information of having an outlier versus not, and that could be beneficial, but could be also detrimental. If you assume all outliers are bad and should be discarded, you might be discarding some useful pieces of data. Now, is it useful piece of data? Is it not? Is it too weird? That's a decision you need to make based on standard operating procedures or advice from somebody who makes the decision. But that's how you do it in the mathematical sense. This is how you calculate the borders for what is and what isn't an outlier. Let's see, any questions? I'm not seeing any questions. All right, so that would be this would be about end of chapter 2. So yeah, let's call this, and I think I am going to call this, then close the stream down, then take a 5-10 minute breather, and then I'm going to start on chapter 3 while I'm still feeling really kind of empowered on it, and then we can do about an hour of chapter 3, and hopefully that will cover enough to keep us happy. So I'll see you soon.